All right, let's dive right in. Picture your typical app running in the real world today. You've got all these different processes. Maybe they're running on completely different machines or even in different data centers halfway across the globe, right? And they're all trying to work together to deliver this perfectly seamless experience to the user. But here is the fundamental challenge of literally all distributed systems. These independent processes absolutely do not share memory. Now, when you execute code locally on your own machine, passing data around is a breeze. You just hand over a memory pointer. Simple. But a memory pointer is essentially just a physical hardware address for a very specific chip of RAM. So, if process A is running on a server in New York and process B is over in London, sending the memory address 0x182b across the ocean, totally meaningless. It's like handing someone a map to a house that exists in another country. Instead, you're forced to take all your rich, complex, multidimensional data structures, those massive trees of user data, nested arrays, complex objects, and completely squash them down. You have to translate them into a flat, one-dimensional sequence of bytes. Sounds like a pretty straightforward concept on paper, but how exactly do we actually manage that complex conversation reliably? Well, that brings us directly to the foundational concept of data flow. If you strip away all the complicated infrastructure of the internet, all data flow basically boils down to one simple action: sending a message. But because of that complete lack of shared memory we just talked about, one process has to do the heavy lifting of encoding the data. Encoding is just taking that rich in-memory object, like a complex C++ gaming profile, and flattening it into a raw sequence of bytes, like a JSON string. Then another process takes on the exact opposite job: decoding. It catches those raw ones and zeros coming over the wire and reconstructs them back into a usable structure. Maybe it reassembles that JSON string into a Python dictionary on the receiving end. And here's the kicker. Deciding exactly who does the encoding and who does the decoding entirely dictates the architecture, the reliability, and the performance of how your whole system communicates. Welcome to this explainer. I am absolutely thrilled to be your guide today. We are going to dive incredibly deep into how data actually moves, communicates, and evolves across modern distributed architectures. So, why does this matter to you? Well, because choosing between these modes of communication is exactly what dictates whether the system you're building can scale to millions of users. It dictates whether it can survive an inevitable network outage, or whether pushing a new feature is going to go smoothly or just crash the entire application at midnight. We're going to thoroughly examine the three primary modes of data flow that define almost every single complex system you interact with today: databases, REST, and RPC services. Here is our roadmap for today's explainer. 1. The data flow challenge. 2. Databases, messaging the future. 3. REST, the web's language. 4. RPC, the local illusion. 5. Flaws of network communication. And 6. Evolving the data. Let's get right into it. Section 1. Databases, messaging the future. Our first mode of data flow actually forces us to totally shift our perspective. Instead of thinking about sending data across space, like pushing packets over a network to another country, I want you to think about sending data through time. Martin Kleppmann brilliantly frames this in the source material. He says you can think of storing something into the database as sending a message to your future self. In a database context, the process doing the writing is the one encoding the data into bytes, and the process doing the reading decodes it. And honestly, most of the time, this is actually just one single process accessing the database, which means the reader is quite literally just a later future version of the exact same process. Now, imagine you write a user record to the database today, and it just has a first and last name. 5 years pass. Your app gets updated, and the new version of the code strictly requires an email address. If that future version of your app reads the old 5-year-old record and can't decode it because the email field is missing, boom, your system throws a fatal error and halts. Because of this massive time delay between writing and reading, backward compatibility isn't just a nice-to-have feature, it's an absolute structural necessity. If your future self can't decode what you wrote yesterday, your entire system architecture is fundamentally broken. Section 2. REST, the web's language. Let's transition to our second mode of data flow and see how this shifts from communication through time back to communication across space. Here, we're talking about processes communicating over a live network, and they're almost always split into two distinct roles: clients and servers. The servers expose an API, and the clients connect to make requests. And the undisputed heavyweight champion design philosophy for these services is REST. REST acts as the standard language of the web because it completely leans into the underlying principles of HTTP. It heavily emphasizes incredibly simple data formats. JSON won the web largely because it's human-readable and universally supported across basically every programming language on Earth. REST uses standard URLs to logically identify resources.
But perhaps most importantly, it natively leverages built-in HTTP methods. Because we use standard HTTP verbs, like get to fetch data or post to create data, developers don't have to reinvent the wheel writing custom commands for every single service they build. It gives us a universal vocabulary. Things like caching, authentication, and error codes, they're all baked right into the protocol itself. And since the client and server still need a way to agree on the specific application details, developers rely on standard documentation tools like OpenAPI. By writing out service definitions in JSON or YAML, every team knows exactly what endpoints exist and exactly what data models to expect before a single line of code is ever even written.
Section 3. RPC, the local illusion. But REST is definitely not the only way to build an API, and that brings us to our third mode, Remote Procedure Calls, or RPC. RPC is actually a surprisingly old concept. It originated way back in the 1970s, and it attempts to do something highly ambitious. It tries to hide the network entirely through a software abstraction called location transparency. Let's starkly contrast these two approaches because they represent a massive philosophical divide in how engineers view distributed systems. Part of the real appeal of REST is that it embraces the boundary. It actively forces the developer to treat state transfer over a network as a messy, distinct process completely separate from a local function call. RPC, it takes the exact opposite approach. It tries to make a remote network request look exactly like calling a local function or method within the same code process. It's an incredibly alluring dream for developers. I mean, writing code that simply says paymentservice.chargecard looks perfectly clean. You don't have to see the IP addresses, you don't have to worry about port numbers, and you completely avoid manually dealing with JSON parsing. It sweeps all that plumbing entirely under the rug. It's a deeply comforting illusion. But, as we're about to see, treating the chaotic network like a safe local computer is an illusion with some incredibly dangerous consequences.
Section 4. Flaws of network communication.
We have to ruthlessly deconstruct this alluring location transparency illusion, because a network request is wildly different and infinitely more chaotic than a predictable local function call. Let's look at the absolute unpredictability of network infrastructure. When you call a local function on your own laptop, it's predictable, right? It takes the exact same amount of time to execute on every single run. But a network request, that is completely outside of your control. First off, latency is wildly variable. A request might take 1 millisecond, or, if a router in a data center halfway across the country catches fire and traffic has to be rerouted, it could hang for 30 seconds. Second, let's talk about passing objects. With a local function, you instantly pass a memory pointer. Done. But over a network, a massive object has to be fully copied, squashed down into bytes, transmitted, and rebuilt entirely from scratch on the other side. That's a huge performance headache for large mutable data. Third, the client and server are often written in completely different programming languages. So RPC frameworks have to translate data types across these languages, which leads to incredibly ugly edge cases. For example, say a Java backend sends a massive 64-bit integer ID over the network, but if a JavaScript frontend receives it, well, JavaScript's built-in numbers max out safely at 2 to the 53rd power. So that ID gets silently rounded, precision is totally lost, and your user's data is corrupted literally without warning. But the most dangerous reality of all, the silent timeout. A local function will either return a result, throw an exception, or crash the program entirely. You always know what happened. But a network request might just vanish into the void, returning absolutely nothing, leaving you completely blind. Let's play out this specific silent timeout scenario, because this is really the intellectual climax of why the network is so incredibly tricky to work with. Imagine a user clicks buy on a $500 shopping cart. Your system makes an RPC request over the network to the payment server. You wait, the loading wheel spins. You don't hear back, so your system naturally times out. It just assumes the network was congested. Naturally, your code is programmed to automatically retry a failed request. Makes sense, right? But what happens if the original request actually got through perfectly? What if the payment server successfully charged the credit card, but it was only the success response packet that got lost in a congested network switch on the way back to you? By automatically retrying, you just sent a second, identical charge card command. That customer is going to wake up tomorrow morning to 2 $500 charges on their bank statement. Trust is ruined, and you've got a massive customer service disaster on your hands. And why? All because the system assumed a remote network call was just as safe as a local function call. To solve this exact disastrous scenario, we have to build in a critical mechanism called idempotence. Think of idempotence like the button for an elevator. You can press the floor 5 button exactly 1 time, or you can mash the button 10 times in frustration because you're running late. The outcome is exactly the same either way. You only go to floor 5 once. That is idempotence. In distributed systems, it's a mechanism for deduplication built directly into the protocol to ensure that retrying a failed request doesn't cause multiple executions. To make this work over a live network, you usually have to generate unique transaction IDs, like a massive random string of characters, and send that along with the request. The server then has to check a database and say, have I seen transaction ID 8F2A before? Ah, yes, I actually processed that a minute ago, so I'll ignore this duplicate retry and just send back the success message again. You simply do not have to build complex database lookups and deduplication mechanisms for standard local function calls. This definitively proves why trying to make a remote service look identical to a local object is just missing the point. The network is fundamentally different, and it absolutely demands a different approach.
Section 5. Evolving the data. So we've established the mechanisms of communication and the absolute chaos of the network. Now we have to look at the compatibility rules we're forced to follow when we actually try to change our code. Remember the ultimate goal of evolvability. We want to upgrade individual parts of our system piece by piece, completely independently, rather than having to shut down the entire internet to deploy an update. As we discussed earlier with databases, the writer usually updates before the reader, so backward compatibility is the primary rule there. The new reader has to understand older data. But for data flow through live services, whether you choose REST or RPC, we generally make a simplifying assumption. Servers are usually updated by the engineers first, and clients, like mobile apps running on millions of individual phones, are updated second. Because of this independent update cycle, we're bound by a strict dual compatibility rule. Let's make this concrete. Imagine you update your server to add a cool new profile picture field. First, the server must have backward compatibility for incoming requests. This means if an old client app sends a request completely missing the profile picture data, the server has to say, "That's fine. I can still process this, I'll just use a default image." Second, the server must also have forward compatibility on its outgoing responses. When the server sends a shiny new response containing that profile picture URL back to an old client, the old client's code must be robust enough to say, "I have no idea what this profile picture field is, but I'll safely ignore it instead of throwing a fatal crash error." This delicate dance of forward and backward compatibility, it's the unsung hero that keeps a modern digital world running smoothly during endless daily updates. We've covered a massive amount of ground today. We navigated from the time travel nature of database storage to the spatial network standards of REST, right through to the deeply complex illusions of RPC. Our core takeaway here is that while modern developer tools try incredibly hard to hide the complexity of distributed systems, the network is always lurking right there beneath the surface, and it demands your absolute respect. It requires careful encoding, strict forward and backward compatibility rules, and complex mechanisms like idempotence to prevent absolute disasters. So I want to leave you with this final provocative question. Take a hard look at your own code bases. Are your remote network calls disguised as safe, innocent local functions? And if they are, have you truly accounted for the unpredictable latency, the language mistranslations, and the terrifying reality of the silent timeout when the chaotic network inevitably gets in the way? It's something every single engineer building a distributed architecture needs to constantly reevaluate. Thank you so much for joining me for this explainer, and I really hope this deeply structured breakdown gives you a much clearer lens through which to view how your systems actually talk to each other.